Welcome to the second part of chapter 5. In this part, we're going to first introduce a very commonly used distribution called the normal distribution. Then we're going to move on to talk about how to derive the distribution of a function of a continuous random variable. Okay, so to get us started, the definition of a normal distribution, okay, so you will see here that now, because we're working with continuous random variable, we focus on its PDF, right? Probability density function, as opposed to PMF, which is the probability mass function only for the discrete random variable. So we focus on the PDF, okay? And in order to have a normal distribution, okay, in particular, the normal distribution has two parameters, the mean and the variance sigma, okay? So if a random variable has a PDF like this, then it is a normal distribution, okay? So the form is certainly much more complicated than the uniform continuous random variable that we have seen before, okay? So just to see different pieces here. So the variance, okay, sigma squared appears here as well as here, okay? And the mean is only up here, okay? And again, this is quite complicated, the PDF itself. And we will see certain properties of it. But as you will see that most likely we're going to use it to do calculation for certain quantities, okay, which we're going to show an example coming up. But regardless, note that this is how a normal PDF should look like, okay? Then if you have a particular mean and a particular variance, then what you do, right, is you replace those quantities with the known stuff. And then for a particular X value that you're interested in, then you should be able to calculate PDF at that point. Okay, so that's what we here have, that if I know a particular normal distribution with mean, mu, and sigma, then I want to know the PDF, right, probability density function at a particular X value. Then what I do is I plug in the mu and sigma square, as well as my value that I'm interested in right now, which is on the real line. Then you're able to calculate the PDF at that point, okay? Again, PDF is not probability itself, okay? The PDF is only telling us how likely the random variable is going to take around that value, okay? And we know that for probability, for a continuous random variable, so this is just a quick review, for a continuous random variable, this is always 0, right? The value of the random variable taking any particular value is always 0, okay? But the PDF is telling us how likely it's going to take around that value, okay? All right, so also, many of you probably have seen this type of graphs before, okay? So for a normal distribution, what's special about it is that it's asymmetric, okay? And unimodal as well, and it's bell-shaped, okay? So here we're using a plot showing 4 different normal density or normal distributions, okay? The 3 of them center at 0 because their means are 0. So it's the yellow one, the red one, and the blue one, okay? So you see that all of them are centered at 0 because their mean is 0, okay? So that's what we mean by the symmetric and unimodal, okay? Only one mode, meaning that the most likely value is only at one value. And it's symmetric, okay? If you flip it around, like according to this x equals to 0, then it's symmetric on the right-hand side to the right, to the left-hand side, okay? And what's special here is that comparing the 3 different normal distributions centered at 0 with mean 0, we see that the only other difference is, or I should say the only difference among them is the standard deviation or the variance, okay? And in particular, the blue has the smallest, okay, variance, okay, whereas the yellow one has the largest variance, okay? So just to keep in mind, again, this is a quick review as well, the variance or standard deviation, they're helpful to describe the spread of the distribution, okay? So if the standard deviation or variance is small, like this one, then the spread of the distribution is smaller. Like you can see here, roughly, it goes from like negative 1.5 to positive 1.5-ish, okay? Whereas if I go to my sigma to be 5, okay, then the value goes from, well, further up, or like further away, right? So this is what we mean by the spread, okay? And because the area under each of the normal curve should integrate to 1, that's what the probably we're gonna show soon. So that's why if I have a smaller spread like this one, okay, then I'm gonna have a taller peak, okay? If I have a larger spread like this one, then I will have a shorter, okay, peak, okay, because the area under the curve should be the same, okay? The last one over here is that having a sigma square equals 2.5, okay? And so it's in between those two types. But then mu is also different from 0. In this case, mu is -2. So you will see that wherever the mean is, that's where the normal distribution is going to center at, okay? And then, of course, the height of the density function or the curve, as well as the spread of the density curves or the density, the function itself, depend on the sigma square, okay? All right, so I was saying earlier that, well, the area under the curve should integrate to 1, okay? So that's because the normal PDF, is well defined, meaning that if we are integrating, okay, over the entire real line, okay, and then the PDF, okay, so that's the PDF, okay, of the normal density, you should integrate to 1. Okay, so this is much more involved in the derivation, so it's not required. So you don't need to know. I'm not going to cover it either. But this is a very important result. The first one that we saw here earlier, I was saying that, well, the area under the curve is the same and it should be 1. That is due to the fact that the PDF of normal is well defined. Okay, and but we, even though we are not going to require this particular derivation, but you should know this result and use the result to solve problems. Okay, so let's look at example here. Use the fact that normal PDF is well defined. Sorry about the typo. Calculate the integral. Okay, and well, so this is integral. Looks quite complicated to do if you want to do it brute force, right? Trying to use all of the technique that you know about integration. But one thing we want to say here is that if you look at this function, looks very similar, right? To, well, if you look at here. Okay, so if so this is one thing very important to notice. Like as soon as you see in the exponent, like e to the negative x minus something to the square divided by something, those are constants, for example. So those are a good hint for you to know that, well, it is probably related to a normal density function. Okay, so if I'm trying to figure out the mu here, so x minus mu square, right? X minus 1 square, so I know my mu is 1, okay? And then 2 sigma square equals to 10, so sigma square will be 5, okay? So this is the building block, okay? So we know that this part is part of, okay, not the entire, because we still have this piece, okay? But if you're only looking at the exponent part, this is related to a normal distribution with mean 1 and sigma square variance, which is 5, okay? And don't forget, the normal density, the PDF is well defined, okay? Meaning that, well, whatever the mu and sigma is, I plug in whatever the value is, this whole thing integrates to 1, okay? So as you can notice here, we, let me just start this one more time. Okay, yeah, so this part, right? And the integral is what the question is asking about. Okay, so pretty much if I move this outside, okay, so this constant, whatever the constant is, because sigma, remember we calculated mu is 1, sigma square is 5, okay? So in here, 1 over 2 times pi times sigma square, so it's 10 pi, right? And then, so let me do this, okay. This is probably easier, okay. So this constant, right, integrate with all of this should equal to 1, okay. So then the question becomes, this is a constant, right? And then, well, this is what we are trying to solve. So we can directly get this whole thing equals to 1 over 10 pi, square root of 10 pi. So this will just be 10 pi, okay. So I include the detailed derivation in here, okay? So just like what I was talking about, recognizing what the mean and the variance are for this normal distribution, and then use the fact that is well defined, so you know that it should integrate to 1 with all of the pieces, okay? So the question is only asking about one of the pieces, and you know that the other one is a constant with regard to x, so you're able to do this using this fact. All right, lastly here, earlier we show on one plot, right, like four different normal distributions. But I just wanted to show you that, well, if you look at one graph at a time, they all look very similar, okay? But if you put them together, then you will see the differences. So the two here is mu0 sigma square 1, okay? And then mu19 sigma square 16. So if I put it separately, right, like even though the general shape and height looks the same, but of course, if you look at the range of the distribution, right, it tells you something, right? And the height, well, it's hard to say because the y-axis is not plotted, but if I do them on the same plot, as you can see down here, okay, so clearly, okay, whatever is centered, right, is at the mean. So here should be 19, okay, that's where the mean is, okay, for this distribution, okay. And just like what we were talking about earlier as well, not only the mean, we can tell from the normal density plot, but at the same time, the spread of it is always controlled by the sigma square. Okay, so sigma square equals to 1 for the left, equals 16 for the right. The left is much more, has a much more smaller spread because of smaller sigma square. So it's much more concentrated, okay, much more concentrated around 0, the mean, whereas this one is much more spread out compared to the one on the left, okay? But regardless, okay, area under the curve, if we do the integration, which is what we know just now, the normal PDF is well defined. So if I integrate this function on the entire real line, meaning that I'm getting the area under the curve for both of them should be 1. Okay, so that's why if you have a taller, right, more concentrated PDF function like on the left, and then if you start to have a larger spread, then well, because the area under the curve has to be 1, so it's going to be a small, or like I should say, like a shorter height as well.